So, welcome back. We wanted to talk a little bit about consistency, and logicians lay a great store in consistency. I mean, if a set of sentences is not consistent, then you can pretty much give up on that essentially. So, let us see why that is the case. Luckily for us, we are convinced that the surgeon story was consistent. So, whatever we conclude from that can be believed. A knowledge base is said to be inconsistent if you can derive alpha and also not alpha at the same time. So, you are saying that alpha, I have a proof of alpha and I have a proof of not alpha. This can only happen if the knowledge base is inconsistent. And the thing is that if you can derive a contradiction that alpha is true and not alpha is also true, then you can practically say anything and get away with it. We can derive anything from an inconsistent knowledge base, and let us see how. That is a very simple process. Let us say that our knowledge base derives to the sentence P and not P. So, the knowledge base is unsatisfiable essentially, and somewhere in that derivation we could derive P and we could also derive not P. So, if we are given this, then we can know that P is true, or we already knew that P is true and not P is true. But if you are just given P and not P, you can use the rule of simplification to say P is true and not P is true. And then you can use the rule of addition by saying not P or Q is true. What is Q? It's some random formula that you can add, and logically it would be true as well. Because if you remember the semantics of the OR statement, OR statement says that either not P must be true or Q must be true. Not either. At least one of not P or Q must be true. And since not P is true, then this whole statement not P or Q is true. But if not P or Q is true, and if P is true, so that is where the contradiction comes into play. You can infer Q using destructive syllogism, or you could have converted this into implication and use modus ponens, but you can prove Q. So, they say that you can derive anything from an inconsistent set of sentences or from an inconsistent knowledge base, and therefore, we must be very careful that our knowledge base is consistent. So, let us talk about this landmark event in logic. In 1931, the German logician, philosopher, mathematician, whatever, Kurt Gödel published his incompleteness theorem. So, it is called as Gödel's incompleteness theorem, which dashed the hopes of formalizing all mathematical knowledge in one formal system. So, up to that point, people were saying that how can we formalize all mathematics and put it into one large axiomatic system and so on. And what Gödel came and inflicted a big blow on the community and said that this cannot be done. You cannot have one large formal system in which you can derive all true statements of mathematics. We will not have time to go into the intricacies of Gödel's incompleteness theorem, because first of all it does not apply to first order logic, and we are interested in first order logic because most of the stuff that we are doing is in first order logic. It applies to systems which are more expressive or more powerful than first order logic, but it says that you cannot formalize everything into one large axiomatic system. So, I am just quoting, I will give you the cite in a moment. This theorem established that it is impossible to use the axiomatic method to construct a formal system for any branch of mathematics containing arithmetic that will contain all its truths. What does it mean? That you cannot build an axiomatic system. An axiomatic system is a proof system which will not entail all its truths, which means that it will not be complete. In other words, no finite set of axioms can be devised that will produce all possible true mathematical statements. So, no mechanical or computer like approach will ever be able to exhaust the depths of mathematics. In those days when Gödel was proving this, computers were just on the horizon. There is a second incompleteness theorem that shows that a formal system containing arithmetic cannot prove its own consistency. So, what Gödel was essentially saying that you cannot have powerful enough systems. By systems we mean axiomatic systems or logic systems, which are both complete and consistent essentially. So, the key word is powerful enough. It does not apply to first order logic, it does not apply to propositional logic. In both of them we can construct systems which are consistent and complete essentially. Complete in the sense that whatever is true can be derived essentially. But what Gödel said that for powerful enough systems you cannot do that essentially. For more expressive systems we will get a feel of that, though we will not go into the formal stuff here. You can look at this Britannica site from which I got this particular quote, and here is another quote I got from another site. And you can go and look at that site also if you are more interested in Gödel's incompleteness theorem. So, as I said, there were two theorems. The first theorem says any consistent formal system F within which a certain amount of elementary arithmetic can be carried out is incomplete. There are statements of the language of F which can neither be proved nor disproved in F essentially. So, when you say that they can neither be proved nor they can be disproved, it is not the case that you take the negation of the statement, then you would be able to prove it also. Neither is possible. This incompleteness was the result of self-reference. Gödel showed that any powerful enough axiomatic system that existed, there existed statements that were undecidable. And what were these statements? These statements had to do with self-reference essentially, and Gödel gave a procedure of Gödel numbering, and he showed how you can construct a sentence like that, that you give us any powerful enough axiomatic system, and Gödel will show you how to construct the sentence which is undecidable, for which you cannot either show that it is true or it is false. These sentences have to do with self-reference. That is why they are powerful enough. In less expressive languages, you cannot talk about self-reference essentially. I keep talking about Hofstadter and his work. So, his book Gödel, Escher, Bach is an insightful journey into self-reference. As the title suggests, it talks about mathematics, and that is why Gödel is there in the title. It talks about art. So, there was this artist Escher who did these engravings, and his engravings had this property of self-reference essentially. So, he had this figure. So, just look up Escher and you will get to see some of these nice paintings. You have things like a never ending staircase. It looks like it is a loop, but it is also a staircase which is going up and up and up essentially. So, in some sense the staircase comes back to itself, or there is this never ending waterfall. The water is falling and then going back and coming back and falling again. Of course, these are kind of deceptive paintings in the sense that they cannot exist in the real world, but Escher kind of did a lot of this self-referential kind of work. And according to Hofstadter, Bach also had a lot of self reference in his musical compositions, that there were things that talked about themselves kind of recursively and things like that. We do not have too much time to go into this, but I would encourage you to look at Gödel. It's a book. It's not a small book to read, but it's worth your effort. His more recent book, which I had mentioned sometime earlier, called I Am a Strange Loop, goes into this self reference in a little bit more compact fashion, and that I am a strange loop refers to this self reference. And the I in that refers to this notion of the self that we have, that I am a person, I am talking, you are listening to me, and that kind of stuff. Bertrand Russell was one of the people who was involved in formalizing all of mathematics. He wrote the Principia Mathematica and so on. But he also recognized that there were certain things that would lead to contradictions. So, he has this paradox which shows that every set theory that contains an unrestricted comprehension principle, can a set be a member of itself, for example. These kind of statements are difficult to deal with, essentially. They lead to contradictions, essentially. So, I had mentioned some time ago that I am lying is not a sentence, because you can't give a truth value to this. If you say it is true, that means you are lying. That means what you are saying is that I am lying, that must be false, and that kind of stuff. Also associated with Russell is the Barber's paradox, though he himself said that somebody else had shown it to him. But you can say it is derived from Russell's paradox, and we often associate it with Russell. What is the Barber's paradox? It says that if the barber is a person who shaves everyone who does not shave themselves, then does the barber shave himself? So, you can see this subtle self reference here. So, if he is shaving himself, then he cannot shave himself, because by definition of a barber, it is a person who shaves people who do not shave themselves. So, if he is shaving himself, then he cannot shave himself, but if he does not shave himself, then he could have shaved himself, because no, he is not shaving himself. So, it is a very interesting kind of a paradox that you should kind of ponder over it for a little while. So, I would like to give you some intuition on how this self reference can cause a problem in formal systems. Imagine that there is a machine which derives all true statements. Of course, that is the goal that we have. Remember, we want to construct a logical machine which is sound and which is complete. When you say complete, we mean it derives all true statements. The example that I am about to give you was given by Raymond Smullyan, whose books are another set that I would very strongly recommend that you go and look at the book. One of the books I have already given a reference and a link to, called Logical Labyrinths, but he wrote many other interesting books, essentially, which were to do with logical puzzles and stuff like that. So, in the example that Smullyan gives, he used the word printed, essentially. So, he says imagine a machine which prints every true statement, essentially. It is like saying derive every true statement. So, we will use the word derive, though in his example he used the word printed, perhaps because he wanted to be careful not to go into mix up things with the more formal meanings of derivation and so on. So, in his world there was a machine that printed all true statements. We will use the term derive. So, here is something that he started with. He defined the conjugate of a sentence, and he denoted it by C alpha. C stands for conjugate. So, a conjugate of a sentence is basically a sentence of the kind alpha hyphen alpha, essentially. So, that he called as the conjugate of the sentence. Then he derived the following formulas. D alpha, it says that alpha will be eventually derived if this sentence is true. So, if d alpha is true, then alpha will be eventually derived essentially. So, you can see that it's talking about sentences. In first order logic, we do not talk about sentences. In first order logic, we talk about terms which are elements in some domain, which map to elements in the domain. But here Smullyan is talking about a language in which you are talking about sentences. So, it is definitely a more expressive or a higher order language. So, d alpha says that alpha will eventually be derived. So, if d alpha is true, then it will be derived. So, it is like a complete system that is what we are trying to say. Then he says n alpha. It says that if n alpha is true, then alpha can never be derived. It cannot be derived. So, in some sense you can see that it is talking about which sentences can be derived, which sentences cannot be derived. Then he says derivable or printable, as he said, the conjugate of alpha is that alpha hyphen alpha, which is the conjugate of alpha, will eventually be derived if this sentence is true, DC alpha. So, if DC alpha is true, then at some point alpha hyphen alpha will be derived or printed. That is what Smullyan said. Maybe printed is a better analogy to think of here. And finally, if you say NC alpha, it means that if NC alpha is true, then alpha cannot be derived at all essentially. So, given these sentences, if you accept that this is your formal system, it tells you which sentences will be printed, which sentence will not be printed. So, you look at a sentence, and if it is true, then you know it will be printed. If d alpha is true, then you know it will be printed. If n alpha is no, then you know that it will not be printed. Likewise, for the conjugate of sentences essentially. So, if DC alpha is no, then you know that alpha hyphen alpha will be printed at some point. If NC alpha is true, then you know that alpha hyphen alpha will never be printed in something. So, what we are going to say now is a kind of an insight into the kind of stuff that Gödel was talking about. Is to there are certain things that you can produce in a formal system which can kind of leave you stumped. So, here is a question: what happens to the NC alpha? So, remember NC alpha is that alpha hyphen alpha will never be printed when alpha is NC. After all, it is just a set of characters, I think. Now, you should think about this a little bit. You can see that if you are saying NC alpha, and when alpha is NC, we are NC alpha says that the conjugate of alpha will never be printed. NC says that one cannot derive the conjugate of NC. Okay, so, just we have substituted NC for alpha. NC alpha says the conjugate of its argument can never be printed, but if we say NC, then we are saying the conjugate of NC cannot be printed. What is the conjugate of NC? The conjugate of NC is NC itself. So, you see what is happening here. If NC is true, it is saying that it can never be printed. That means it is not complete, this system is not complete. That here is a true statement, but it cannot be printed because the statement itself is saying that it cannot be printed or derived essentially. So, this is just to give you a flavor of this kind of strange loops that Hofstadter talks about and Russell talks about and Smullyan talks about, which was originally spoken about by Kurt Gödel when he gave his incompleteness theorem. It put an end to this whole big exercise of trying to formalize everything in mathematics essentially. Okay. So, we have talked about propositional logic, we have talked about first order logics. We will look at a couple of more logics in this course as we go along. Here is a kind of a glimpse as to what else exists. Second order logics allow us to quantify over predicates essentially. In first order logics, we could quantify over variables. We could say for all x, for all y and things like that. In second order logic, you can quantify about predicates, that for all predicate symbols or something like that. And one interesting sentence which has to be classified as second order logic is the principle of mathematical induction, the first principle of mathematical induction. What it says, if you remember, is that if the predicate is true for some base clause, let us say 0 or something, if you are talking about natural numbers, and if you can show that p of x implies p of successor of x, then between these two things it is enough to show that for all x p x is true essentially. This is the principle of mathematical induction. The only thing we are saying here is for all p, any, if you can show this for any predicate, if you can show that the base is true and the induction clause is true, which means that p of x implies p of successor of x, then for all x p x is true. And you can see that this uses in some sense a higher order logic. We are saying for every predicate this is true. There are other logics which are more expressive than first order logics. So, there are modal logics. The sentences have a modality, and the modality is that of either necessity or possibility. So, there are two modalities in modal logic. One is that as box alpha, which is drawn with a box before alpha, and it says that the sentence is necessarily true or definitely true. The other is diamond alpha, which is drawn, which is represented by drawing a diamond before alpha. So, here is diamond alpha and here is box alpha. Diamond alpha says the sentence is possibly true. Truth values are still two valued, either you are true or you are not true, the sentence. What this says is that the sentence may be true or the sentence, we are not like definite that it is true essentially. Then there are these epistemic logics and doxastic logics, which are useful especially when you talk about multi-agent systems. And it uses two modalities. One is called the knowledge modality, one is called the belief modality. The knowledge modality says that K A alpha stands for agent A knows alpha. The belief modality says agent A believes alpha. So, there is a difference between knowledge and belief, and from the logic perspective, knowledge can only be about true facts, that if you know something that it must be true. Belief can be about facts which are not true. So, for example, I believe that the earth is flat. That does not mean that the earth is flat, but if I know some formula alpha, then that formula better be true in my domain. And so, there is a subtle difference between these two modalities. Temporal logics are also logics which talk about modalities, and they say this alpha is true at certain time essentially, t essentially. Event calculus is a higher order logic which talks about time, action and change essentially. We will look at event calculus a little bit later in this course, and we will also look at epistemic logics a little bit later in this course, I think. But let us get back to FOL, which is, as I have been saying, is going to be the main part of our course. In first order logic, we can build logic machines that are sound, provided you use valid rules of inference, and we have seen how to define valid rules of inference. They are complete, and we have not proved that the resolution refutation method is complete, but we have accepted the proof that it is complete essentially, the proof given by Robinson in 1965. So, in first order logic you can build complete systems, you can build consistent systems as long as the knowledge base is consistent. Whatever you derive from that will be consistent, and you will never be able to derive alpha and not alpha at the same time. Of course, we have not given a proof of that, but we cannot put too much into one course. As we will see, first order logic is semi decidable. What do we mean by that? We said propositional logic is decidable at some point. Decidable means that you give a knowledge base, you give a query, and the algorithm will terminate saying yes or no. When we say semi decidable, and that happens to be the case for first order logic, and we will see examples when we try to look at it from the logic programming perspective, is that the theorem prover or the algorithm which is proving theorems will halt if the query is true. So, in that sense it is complete, but if the query that you are asking is not true, then it may never halt and may go into an infinite loop. So, that is a property of first order logic, and it should not be surprising to you, because you can always write programs which go into infinite loops, and programs are, as we will see, nothing but sentences in first order logic. Though they do not always look like that, but anything that you can do in a procedural language you can also do in logic, and we will see this as we go along. What is more important is that first order logic is intractable, that even when we can find proofs. So, we say that it is semi decidable, that if there is a proof it will find it, but there are situations, because the language is rich enough, is that sometimes proofs themselves can be exponential in length. So, just imagine that if the proof is exponential in length, then the proof finding process, which is searching for that proof, will be doubly exponential. So, sometime in this course, a little bit later, we will look at two tractable subsets of first order logic, and the first one will be horn clause logic, which is what we will study next, followed by showing that horn clause logic leads to logic programming, which leads to a language called like Prolog, which is an implementation of logic programming, and it works well for a subset of clauses called horn clauses, which we will see pretty soon. Another subset that we will look at is description logics, or the logics of noun phrases essentially. These description logics have become very popular nowadays because of the fact that they are used to build ontologies, and ontologies are basically collections of noun phrases which talk about categories and subcategories and things like that. So, when you say all men are mortal, in some sense we are talking about noun phrases, that the set of men is a subset of the set of mortal features. But ontologies allow you to talk about more well defined categories, which are described in these languages called description logics, and they have very efficient rules of checking whether one category is a subset of another category. So, we will spend some time looking at description logics and ontologies later essentially. So, we will end with this FOL here, and then we will come back to a subset of FOL and also kind of draw attention to the fact that what you do in logic is equivalent to what you can do in computing. So, that is all for now. We will see you soon.